And we are back. Welcome back from your weekend. Today we will continue on and complete our conversation for this module on validation. But before we begin, let's go over some administrative information. And I'll also begin at this juncture by setting my pen color. Let me select blue. All right. So the reading, again, Chapter 4 is the focus of this module on dealing with noise. 4.1 section is overfitting, 4.2, section 4.2, regularization, and 4.3 on validation. Please make sure you're keeping up with reading. Also, homework 3 on neural networks will be due today on 31st of March, 2020 at the usual 1 second before midnight, 11:59 and 59 seconds. So where we last left off, we talked about this idea of optimistic bias, and we used the example where because you're using your validation set to select the best from among a set of hypotheses, it can give you the impression, because you're searching for the best, it can give you the impression that error is actually much smaller than it really is. And this optimistic bias was illustrated where we left off. We had two hypotheses that each have an out-of-sample error of 0.5. And we had an error estimate for each one. We called E1, the error estimate for H1, and E2 is the out-of-sample error estimate for H2. And so error, of course, can be between 0 and 100%. So E1 and E2, as far as distribution of error is concerned, is uniform in the closed interval between 0 and 1 on the real number line. And so if you're trying to select from the best hypothesis from this set of two hypotheses, H1 and H2, well, certainly you're going to take the hypothesis whose out-of-sample error estimate is going to be smaller. So E is the minimum between E1 and E2, this expression. And so the ask that we had from last time is, what is the probability that your error is going to be less than 0.5? Well, if you're taking the minimum, that between E1 and E2, that means either E1 is less than 0.5 or E2 is less than 0.5. And so we took those cases to look at what this probability is, and we found that the probability that at least one of them, because at least one of them has to be, these errors has to be less than 0.5 in order for the minimum to be less than 0.5. So we take the two cases where we have E1 is less than 0.5, and we have the other case where E2 is, that should be 2, is less than 0.5. We also consider all the other scenarios that can happen. We can have E1 is greater than 0.5, while E2 is greater than 0.5. Now, of course, for that case, we're going to have the minimum is going to be greater than 0.5. But then we can have this other scenario, E1 is less than 0.5, and at the same time, E2 is greater than 0.5. Well, that satisfies the case that at least one is less than 0.5. And then we also have the converse, E1 is greater than 0.5, and at the same time, E2 is going to be less than 0.5. So if we take these four cases, well, for this first case, yeah, that satisfies that one of them is less than 0.5, check. The second one, no, that doesn't satisfy. This one satisfies. E1 is less than 0.5, okay, check. Likewise, E2 is less than 0.5, check. So that means 3 out of these 4 cases, we have one of them is less than 0.5. So that means we have a 75% probability, because that's 3 cases out of the total 4 that satisfy this one of them, this condition, is less than 0.5. So this whole idea of optimistic bias in this particular case, even though out-of-sample error for each one is 0.5, by the sheer fact that you're selecting the minimum between the two, your chances that your best hypothesis, the one that has the minimum error, being less than 0.5, is going to be a 75% chance. And so this is your so-called optimistic bias, where we left off last time. Okay, continuing on, let's take a look at validation error for use as model selection. And so here we have a bunch of hypothesis sets, H1, H2, up to including H sub m. And so your hypotheses that you're going to consider, you're going to have m many of them. So these hypotheses, what a hypothesis is in this case, can be one of many different things. So for example, H1 could be a degree 2 polynomial, degree 2 poly. H2 could be a degree 3 polynomial. Likewise, the next one could be a degree 4 polynomial. And then lastly, we could have a degree, let's call this m plus 1 polynomial. I should have just said degree 1, degree 2, and so forth. But nonetheless, you can have a different set of functions as your different m many hypotheses. You could also have the same hypothesis. Let's say you had a degree 10 polynomial, but your regularization parameter, lambda, was 0.001. And then you could also have another degree 10 polynomial, where your regularization parameter is lambda equals 0.01, ... And this last one is the same degree 10 polynomial, but with a regularization parameter of lambda equals, say, 1.0. So these are all different models. You could have a different degree polynomial. You could have the same degree polynomial with different lambdas. You could also say this H1 is a neural network. This one is, say, a linear model. This one might be non-linear regression, for example. They could be completely different algorithms and function families. And so there are many different ways that you can pose these different hypotheses, and the only requirement is that you have big M many of them. Okay, so now what we're doing, of course, we take our original data set, D, and we divide it into two pieces. We set aside some subset of size K, our validation set, that's D val, and then the remaining set, D train, of size N minus K, we're going to use to train each one of these versions of the hypothesis. So you use D train. The result of that, when learning finishes, or the learning algorithm halts, you're going to get what we call GM minus. Now again, because each one of these hypotheses trained on a limited or smaller version of the training set, we call it GM minus, where M, our index, ranges from 1 to big M because we have big M many hypotheses. This GM minus, this notation, that minus is used to represent that this resulting final best hypothesis is limited because the training set we use to train it is limited because we set aside these K many data points for the validation set. So then, of course, we take our validation set, we furnish it, and we use this validation set to evaluate each one of these limited final best hypotheses G minus. So we evaluate the devalidation on G1 minus, on G2 minus, up through and including G big M minus. So that results in our validation error. And the validation error, as we said before, is an estimate of out-of-sample error. So here we have E1 representing the validation error for G1 minus, E2 is a validation error for G2 minus, and so forth, up to and including E big M is the validation error for GM big M minus. And so each one of these errors, these validation errors, the subscript little m, is going to index into those big M many hypotheses. And so EM is equal to the validation error on that limited final best hypothesis, the mth one, GM minus. Okay, so then we take each one of these validation errors and we use that as the criteria for choosing the best limited final best hypothesis. And how do we do that? Of course, as we said before, there's optimistic bias, but we pick the best one. So we look for the smallest EM, the smallest validation error, and we pick that best among these final best hypotheses, these final hypothesis candidates, as it were. So we have our d-val, and d-val is used to select from among these big M many final best hypotheses, GM minus. So we pick the best one, and we're going to call that HM star. So star means it's the best, and it's the best as defined by being associated with the smallest validation error, EM. So this HM star is the best hypothesis among these big M many hypotheses, and it's the one associated with the smallest validation error. So that smallest among the big M many validation errors is, we're going to note this as EM star. Okay, so now we take our full training set, combine, if you will, the training set with the validation set to make our original set of in-sample points, and we run that through HM star, our best of the limited final best hypotheses, HM star. So we do that, and our result, we call that GM star. It is the best version of those GM bars that we get because we now have more training points, and VC dimension and Herfting's inequality tells us so. The more data points you have in which you train, the better the generalization. Okay, so this is our scheme, how we use d-val in order to select the final best hypothesis. And if you think about what's happening here at this validation stage, we have a special hypothesis set here. All the hypothesis set is a bunch of hypotheses. And this special hypothesis set, if you think about it, contains M hypotheses. So that means the size of this hypothesis set, if we were to draw magnitude of it, that's equal to big M. And so what we're effectively doing when we do validation, it's kind of like a second stage learning, right? Second stage. We have a data set, d-val, and we're using this data set to select some final best hypothesis out of this set of hypotheses. And we do that by running it through the first one, running through the second one, running through the third one. And in doing so, we take that eval, that EM, and select the best one. So this is kind of like a learning problem. It's kind of like you learn in the first stage, and then you learn in a second stage. Okay. So let's consider what happens and look at the relationship between the validation error on the reduced or simplified final best hypothesis, the intermediate GM star minus, the best among those candidates, and the out-of-sample error. And so when we get this GM star, each of these hypotheses, if we calculate the validation error, remember that validation error is eval of GM. And so that GM star just happens to be one of these hypotheses that happens to be associated with the smallest validation error. So for that GM minus star, that would correspond to the best of these final best hypothesis, limited final best hypothesis candidates, because we select the candidate and then we run that candidate through the full data set to get GM star. So when we refer to, and in the book, refer to eval of GM star minus, that corresponds to that particular GM minus that we've associated with the final, with the best eval GM, EM, the best validation error EM. And so if you have a validation error associated with that best limited hypothesis that you've selected, if you run the the full training set through that's going to be E out. That is going to be an out-of-sample error associated with that limited final best hypothesis. So let me say that again. You have a limited set of hypotheses. Each one of these is limited because they train on because they are the result of training on dtrain, which is a smaller or more limited version of the training set. So one of these is going to be your GM star minus, and that GM star minus is the selection that's associated with the smallest eval, right? So that's E1, E2, and so forth. So GM star is going to be associated with EM star, right? EM star is the validation error of GM star minus, and I'm just saying GM star minus because that's the G minus associated with the smallest validation error. So we said that validation error is an estimate of out-of-sample error. So that means the validation error associated with the best of these limited final best hypotheses, that's going to be E out of GM star minus. So that's what's referred to in this slide. Eval of GM star minus, the validation error of the best of the final best hypothesis candidates, these limited final best hypothesis candidates, that's going to be a biased estimate of the out-of-sample error of GM star minus, because there's an associated performance out of sample of this GM star minus. And so it's going to be a biased estimate. Why? Because this GM star minus that we select, because it's the result of selecting the smallest validation error, as we said, we get this optimistic bias. So we selected some model HM star, and that HM star, as we said, is the hypothesis set associated with the limited final best hypothesis GM star minus, which was that selection. Because it's a selection, we get this optimistic bias. And so in this illustration, we have two different models. Say you'd have a degree 2 polynomial and hypothesis set and a degree 5 polynomial hypothesis set. And you try sampling a bunch of times, setting aside your validation set, and each time you do this, well, you're going to get maybe sometimes the degree 2 gets selected, maybe sometimes the degree 5 gets selected. Nonetheless, you have two models, and over time, you're going to increase the validation set over a number of runs, and you're going to compute the average, and that's what this blue line is. It's the average validation error of the best selection among those limited final best hypotheses GM star minus. So these are the validation errors, the validation error associated with the winner, if you will, among these GM minuses. Okay, so we plot that as a function, this average across a number of runs. We plot that as a function of the validation set size. So as we go here to the right, the validation set size K increases. Now here, this red line is the out-of-sample error associated with GM star minus. And how you could compute this is by taking your training, your data. You have your training set, dtrain. You have your testing, your validation set, dval. You have your testing set, dtest. So you set aside dtest. Here's dtest. You set aside dval. Dval is going to be used for validation. And then your dtrain, that's what you use for your training. So after you select your GM star minus, you combine your dtrain with your dval. So you combine these two, and you input that here to get your best version of your final best hypothesis, and that's what we're referring to as GM star, because it's no longer the minus, it's now GM star, because we've given it full data set. Okay, the full training set we've given it. So now we have this test set, and now you take this final best hypothesis, the full one, that had the full training set, train, union, deval, and you evaluate it on this out-of-sample data, right? Because it acts like out-of-sample data. This result is E out of GM star. Okay. Now, if you wanted E out of this GM star minus, you would just take this test set and run it on that selection of your limited version of the final best hypothesis. And this is going to give you E out of GM star minus. Okay? So it's showing you the relationship between E out of GM star minus and E out of GM star. And it's all being driven by running this set-aside test set as if it were out of sample data through each version of this hypothesis. So this is out of sample error of the limited best final best hypothesis. It's one of those candidates, and you've estimated out of sample error. So let's see what happens behaviorally. So if our validation set size is smaller, well, what happens when k is small? That means n minus k is big. So if dtrain is bigger, well, if dtrain is bigger, then your out of sample error is going to be smaller. And why is that? Well, because you have a larger amount of data with which to train each one of these versions of the hypotheses. And Hoeffding's inequality in VC bound tells us if you train with a bigger training set, dtrain's bigger, n minus k is bigger, you're going to get smaller out of sample error. So that means the out of sample error associated with this quantity, the GM star, let me fill that in, the GM star minus, that out of sample error is going to be smaller. And so this looks like a reverse learning curve, right? As n gets bigger, that's in this direction, E out gets smaller. As n gets smaller, that's in that direction, going to the right, E out gets larger. So the second thing we look at is this validation set, eval on GM minus. And you might wonder, well, gosh, why is eval of GM star minus getting bigger? Let's see what happens. So as validation set size gets bigger, right, as this validation set size gets bigger, dtrain gets smaller. So if validation set size k gets bigger, dtrain is smaller. And if dtrain is smaller, that means each one of these GM minuses, they're going to have worse performance. So if they have worse performance out of sample, the estimate of out of sample error is also going to be pretty bad. So the reason why this eval of GM star minus goes up as validation set size goes up is because the hypotheses have less data on which to train, and therefore the estimate on error of them is going to be larger, because less data to train means worse performance out of sample, and the estimate of the out of sample error is also going to be smaller. Let's also see what happens when the validation set size gets larger. Well, you notice here that the distance between E out and eval gets smaller and smaller and smaller. Now, the reason for that is, of course, as validation set size gets bigger, it becomes more and more so a better estimate of out-of-sample error. So even though out-of-sample error gets bigger, because there are fewer training examples, the gap between the estimate, eval, and E out is going to narrow. Okay. So E out gets smaller with more examples, more samples in the validation set. Eval gets bigger with a smaller validation set. So with bigger K, the estimate of E out gets more reliable, so they get closer, but the problem is you're robbing dtrain of examples, and therefore you get a better estimate of something that's a worse performer. Okay? All right. So let's take a look at this idea of validation as a weird type of training, secondary training. You have a bunch of models, H1, H2, H3, up to and including HM. And we effectively use deval to select some hypothesis from among a set. And so our set of hypotheses here has M many hypotheses, and essentially our H-val we're using to select either G1 minus, G2 minus, or up through and including GM minus, G big M minus. And so if we think about this validation, this optimistic bias-based selection as a type of training, we are training. Deval acts like a special kind of training set for these intermediate or these limited final best hypotheses. You're making a selection from among them. And if you're selecting among hypotheses, this is kind of like having a hypothesis set, like we talked about earlier in the semester, script H, where it consists of G1 bar, G2 bar, G2 minus, G3 minus, up to and including G big M minus, not bar, I mean minus. And so if you're making a selection using your data deval, well, that's exactly what learning is. And because it looks like learning, we can relate this back to Hoeffding's inequality. And as a learning algorithm, our error for this secondary learning to train the finalist, as it were, that validation error acts a lot like EN, right? It's the in-sample error for this secondary phase of training. So we have E out of our final best hypothesis from the specialized set that consists of all of the limited G's, the G1 minus through GM minus. We select our E out, our out of sample error rather, is bounded from above by this validation error among each of these hypotheses, plus the complexity measure. And this complexity measure involves the size of the data set. So for regular Hoeffding's inequality, this would be n, the size of the data set, and this NL, natural log, ln, would be on the size of the hypothesis set. So the size of our hypothesis set is a discrete hypothesis set of size big M. So we have this big O, radical log of the hypothesis set size over the data set size. And so validation error acts a lot like training error on the specialized hypothesis set consisting of all of our GM minuses. And therefore, it is governed by Hoeffding's inequality. Now, this is for the finite case, right? If you use the infinite case, where let's say you're just doing regularization on a regular learning, you use VC analysis, right? You have your regularization parameter, and you talk about VC analysis because you have an infinite size hypothesis set. And with the infinite size hypothesis set, you reduce this down to the number of dichotomies that can be generated by this hypothesis. And so this is just to say, given a set of models, you can relate back to Hoeffding's inequality and the VC bound for this second round of selection among these limited or intermediate final best hypotheses. Okay. So let's talk about this idea of contamination. When you evaluate error, this contamination is one of the reasons that you're overly optimistic about outer sample error. And that stems, again, from the fact that you're picking the best from among a set of alternatives. Now, if you have your training set is very contaminated. Detrain, every single hypothesis sees detrain. If we go back, we see that detrain is run through the first hypothesis, the second hypothesis, the third hypothesis, big M many times. But if we look at the test set is clean. The test set does not get evaluated until after you're done. When you get this GM star, That's when you take your test data set, dtest, and run it through this GM. That's going to be your E out, right? So the test set is only run through a model once. It's very clean. It's only touched by one model when you evaluate your final result. The validation set sits in between. It's only slightly contaminated. You don't want to evaluate your validation set lots and lots and lots of times. So let's say you're choosing 10 different parameters, not just lambda, but you're choosing lambda and the degree of the polynomial, and you're choosing whether it's a neural network or choosing whether it's nonlinear regression, a bunch of different choices made for using your validation set. You don't want to contaminate it that much. You want to keep your contamination for validation set very slight, or else you will lose the benefit of validation in estimating a good, or providing for a good estimate for out-of-sample error. Okay, so let's take a look at this cross-validation idea. Now, certainly, we said that E out of your final best hypothesis is close to your E out of your limited final best hypothesis if you have small k. And the reason for that is as k gets small, the size of D train, which is n minus k, is large. And if you have a large n minus k, that means by Herfting's inequality and supported by VC bound Herfting's inequality, you're going to get very good out-of-sample performance. If you have a large D train, you have a large D train if your validation error is small. So you want to try to make your k validation set size as small as possible. At the same time, you want to have good estimates of out-of-sample error. And how you get good estimates of out-of-sample error is by having large validation set size, so k large. If k is large, what happens? Your validation error of your limited hypothesis is going to be very close to your out-of-sample performance for that limited hypothesis. And of course, you want that limited hypothesis to be close to your non-limited or your full final best hypothesis. So you, in order to get this relationship, well, eval is close to E out on the limited final best hypothesis if you have large k, because this is a very good estimate of the out-of-sample performance for this G minus. But at the same time, in order to get out-of-sample error for this limited hypothesis G minus to be close to out-of-sample for the non-limited final best hypothesis, you need to have small k. So you need to have k large and k small at the same time. So there's this tension here. K needs to be small. If it's small, you have bad estimates. You kind of break this relationship. If k is large, you have good estimates, but you break that relationship. So how are we going to balance this? This is the role of cross-validation. So we're going to start with the simple case of so-called leave one out cross-validation. So we're going to make a new definition, and this is in the book. In this new definition, we define a limited data set, and this is going to be a special training set that we arrive upon by leaving out just a single in-sample data point. So here we have big N, many data points, label instance pairs, xn, and its corresponding label, ground truth label, assigned by the target function, yn. And we have big N, many data points. And so we're going to say just script D, N, is going to represent D train that we build by leaving out the nth data point. So that means the train in this regard is going to have n minus 1 data points. So if our point is left out, our validation set, dval, is going to be very simple. It's going to consist of just a single data point. So we take this dn, and because we leave one out to form d train, or this dn, we're going to label dn where that subscript n represents the nth data point that was left out when we formed this training set. So we have different versions of this dn. We have a d1, corresponding to the training set that includes x2 through xn. We have D2 corresponding to the training set that has x1, x3 through xn, and so forth. We also have a data set D big N, which corresponds to all of the data points x1 through x big N minus 1. So we have big N different versions of this training set corresponding to the data point that is left out. The data point that's left out is treated as our validation set. It's a very simple one, only has one data point, and the remaining training set, that's our D-train, is labeled as D1, D2, D3, depending on which one was left out as the validation set. So then our final best hypothesis that we learn from the particular Dn, we're going to call that Gn minus. Now Gn minus, this subscript n, corresponds to that Dn. That's the final best hypothesis. That's limited because it doesn't have all n many data points, but it's the final best hypothesis as a result of training on that Dn data set. Likewise, if we look at the validation error, that validation error eval on that same Gn minus is computed by taking that data point xn that we left out and computing the error of that Gn minus. So we take this error at a point, it's very simple, and that is our honest to goodness validation error. Now, of course, it's not very good. Each En describes the expected estimated out-of-sample error. It's not a very good estimate because it's only based on one data point, but nonetheless, it still is the estimate. So now, if we think of each En as being associated with a data point that belongs to a validation set, then it can become respectable if we evaluate that across all of those points. So what we can do then is we could say, okay, let's take the estimate for that first point, for that second point, that third point, that nth point, that out-of-sample error estimate, and let's take the average. And that's our so-called cross-validation error, ECV. So ECV is just the average, 1 upon n, of the sum over all of these different point-wise simple validation errors. That's our average validation error, which we call our cross-validation error. Okay? And because this is over each one of these different validation errors, you can think of that as a kind of validation set that involves all n many data points. So as such, in doing this, because dtrain is as big as we can get it, that satisfies this small k, right, with large training set, because we average over all of the n data points, n of them, that looks like a validation set, and that also satisfies our criteria of having large k. And so this cross-validation error achieves both of those and allows us to make good selections in building, using validation error to select our good best hypotheses while still maintaining great estimates for out-of-sample error. Okay, so let's take an example of what cross-validation error might look like. And this is a simple example. Here we have a linear model, and we've sampled 3 data points from a target function. And now we run this linear model, and we fit it, and we compute this model, we fit it, based on leave one out error. So here, we select these 2 points, this one and this one. We train, we get the following line, the black, and then we compute cross-validation, the leave one out error, the validation error, which is the difference between this point left out. We call that E1, because this is the first data point X1, this is X2, and this is X3. So E1 is a validation error using that first version of the data set. We'll call that D1, right, because we're leaving out the first point. Now here, this is D2, right? D2 consists of this data point, the first one, X1, and the third data point, X3. And when we train on D2, we're training on X1, X3, we get the following linear fit. And then when we compute validation error, eval, it's based on this validation set that just contains the second data point. And likewise, we will call this D3 because we're leaving out the third data point. We're training on X1 and X2, and we compute the validation error using this limited validation set of just E3. So then our cross-validation error is just the average, 1/3 times the sum of E1 plus E2 and E3. Okay, so let's see this in action. We'll go back to an example we talked about much earlier. We have a linear hypothesis set, and we have a constant. So this is a line in the plane. This is just a constant line. And we're going to do this same learning scenario, using cross-validation error, leaving out one data point. So in this first column, we're going to train on D1. The second column, we're going to train on D2. And in this third column, we're going to train on D3. Okay, and we're going to evaluate validation error using E1 here, E2 here, and E3 here. So when we train on D1 for the linear fit, again, we get that line. We get this validation error. When we train on D2, we get this line. We get that validation error. When we train on D3, we get this line. We get this final validation error associated with that third data point, X3. For the linear model, we do similarly, the constant model rather, we do similarly. We train on D1, and so this constant model gives you a y-intercept straight across, which is halfway between the two data points on which we train. So we get this model training on D2. We get this model halfway between the X1 point and the X3 point along the y-axis while training on D2. And likewise for D3, we get this constant model training on X1 and X2. And so if we take all of these errors, these validation errors, we compute the average, 1/3 of the sum of E1 plus E2 plus E3, we see that the constant model ends up being smaller because 1/3 of this E1, E2, E3 is smaller than 1/3 of this E1 plus this E2, this E3. Okay, so this same idea was used, cross-validation, to select among a set of models for the digit classification task. And so let's go back. In this diagram on the left, your left, we have two features. So we're going to have data points in two-dimensional feature space. The horizontal axis is average intensity for a digit image, and the symmetry axis is this vertical axis. And so here we have data points that are not a 1 for digit images using these two features, intensity and symmetry, and these blue circles are data points that are 1 digit. So you could take, digits 0 through 9, and you could categorize them as either being a 1 digit or not a 1 digit, right? Just recast the labels +1, -1 to represent +1 for those that are 1 digits and -1 to represent those that are not 1 digits. So we have 500 of these data points, or rather we sample 500 of these data points, and that's going to be our in-sample data that we're going to start with. And we also have a set-aside data set that we're going to use to evaluate out-of-sample error, right, as we had explained before a couple slides ago. And so we take the original input representation using the augmented X vector, so this would be our X0, which is fixed to 1, and we put that through a linear transformation using a degree 5 polynomial. So here we have 1, we have the individual features, we have the square terms, we have the cross terms, x1, x2, we have all the different cross terms, and here we have x1 to the 5th power, and we have x2 to the 5th power. And so we have a total of 20 features. And so if you think about it, we can choose which version of this model we should use, which feature representation. Should we use the one with 1 feature or 2 features? If we use 2 features, we'd have this feature and that feature. 3 features would be 1, x1, x2. 4 features would be 1, x1, x2, x1 squared, and so forth. So we have 20 different models we can try. And if you think about it, we have H1, that's the first model. H2, second model, up to and including H20, where each one of these models differs in what that representation is. Okay, how many features it's going to use and the type of feature. If we have the full H20 version of the hypothesis set, we have the most complex one with more degrees of freedom. If we have the most simple hypothesis, H1, we have the simplest one with just one, it's a 1D model, right? So with our cross-validation, this leave one out, what we're going to do is use validation error, this cross-validation, to select which among these is going to give you the best limited hypothesis. So we would call this G1 minus G2 minus up to and including G20 minus, where each one of these is arrived upon by inputting each of the D trains. So D train. But this D train is going to be one of 500 different D trains. You're going to input for this a D1, leaving out the first of those 500 points, D2, leaving out the second, up to and including D500. So each one of these hypotheses, when you train, you're going to train on each of these 500 different versions of the training set, where you're setting aside one data point each time, and that one data point is going to differ in what the validation set is. So here, each D train is going to be of size n minus 1, where n is equal to 500. And now this validation error, when you compute eval of each one of these limited final best hypotheses, this one is going to input G1, X1, and then X2, and then X3 as that validation. So each one of these hypotheses is going to be run 500 times, and for each of those 500, you compute the eval on that singular singleton validation set, and then you're going to compute the Crossfold validation error. It's going to be 1 over 500 times the sum. I goes from 1 to 500 of EI, right? Where each EI is just that validation error on that singleton validation set. So you do that for H1, you do that for H2, you do that for H3, and now you're using the cross validation error, ECV, on this first hypothesis, ECV on the second hypothesis, and so forth, and you're using the cross validation error to select which of these 20 hypotheses is the best one. Okay, so if we do that, we take a look at the blue curve, that's your in-sample error. We take a look at the black curve, that's your cross-validation error. And then you also can take a test set that you set aside and compute out-of-sample error. And this out-of-sample error is on the final one, G star, right? So when we do that, some observations. As the number of features gets larger, meaning you're going from H1 to H2 to H3, getting closer and closer up to H20, as you increase the number of features, you notice that in-sample error gets smaller. And why is that? Well, because it's overfitting. A more complex model will start to overfit, and your in-sample error will go to 0. If we look at our E out, well, as E out dips down, cross-validation error as an estimate also dips down. If E out increases, cross-validation error also increases as a function of the number of features used. So that's kind of nice. So let's look at cross-validation error. And we see here, cross-validation error goes smaller, smaller, smaller. And right around 5, maybe 6, this cross-validation error, 1, 2, reaches its elbow, if you will, and starts to increase. So let's say the first point starts to increase. It's right about 5 or 6. So that means at about 5 or 6 features, this model starts to overfit. So this is the best hypothesis, H6, that we can choose based on this cross-validation error. So we use cross-validation here to determine where to stop. Which of these different versions of the model, 20 of them, gives you the best out-of-sample error. And you notice as we start to overfit, we can basically stop. And that stopping is the selection of what is the best G minus among these set of 20 many hypotheses. So we're going to get 20 of these limited final best hypotheses, and we're going to use cross-validation error instead of validation error to select which one is the best. Okay? All right. So when we do this, we notice that we stop at about 5 or 6. And if we go back and do the full fit without validation, cross-validation error, we use the full model, we get the following model, the following final best hypothesis. And so here, we notice that this model, using all 20 degrees of freedom, right, for the H20, it's working really hard to categorize this outlier, and really hard here, bending and twisting and folding, to categorize that outlier as well as over here. If we use the constrained model as informed by cross-validation error with just using 6 features, you'll notice it's a lot smoother here, and we don't spend our degrees of freedom pursuing what look like outliers in the data. And that plays out in sample error in the unconstrained full model case. E in was 0, E out is 2.5% error. And for the version informed by validation error, you can think of it as early stopping. It stops before it tries to use that full model, and in essence, it's learning the feature representation. E in is 0.8%, so we sacrifice in-sample error, okay? But E out is 1.5% with validation. So validation acts a lot like regularization in this case because it's preferring the smoother hypotheses. But it does so not by using a regularization penalty term in the optimization. It does so by estimating E out directly and choosing the version of the hypothesis set that has the best out-of-sample error estimate. Okay, so there was an issue here when we did this leave one out cross-validation. If your data set is really large, you can imagine if you had 1 million data points, well, you're going to train on 999,000 and leave out 1, so that means you have 1 million different D values, 1 million different data sets that you're going to train on. That's not feasible if you have large data sets. So one of the happy mediums that people have developed is so-called CrossFold validation. So 10-fold cross-validation takes your set of data, your in-sample points, and it divides it up into 10 equally sized parts. So you randomize your data and you separate them into 10 equally sized data sets. And then each data set, each sub-data set is considered a fold. So rather than leaving one out, you leave out 1 fold. So if you had 10-fold cross-validation, each one of these Ds represents 1/10 of your data. So it would be N over 10 data points. So you leave out one of the folds, you train on 9/10 N of your data. That would be the size of D train. And then you validate rather on 1/10. So your D val, the size of D val, that should be val, is going to be 1/10 N. And so that's one version of your validation set, depending on which fold you're leaving out. So if you leave out the first fold, you're going to have a D train of size 9/10 of your original data set. And you're going to train on this 1/10 size D1, right? So instead of having D1, that subscript representing the data point, is going to represent which fold that you have. And so then when you compute your cross-validation error, ECV, it's just the average over the number of folds. So the number of folds is going to be K, which is N over 10 for 10-fold cross-validation. And then it's going to be F, the fold, goes from 1 to 10 in this case. And you're going to compute eval of your hypothesis, G, on your particular data set. And I'll just use some high-level notation here. And I'm going to say D val. Okay? And that's going to be the fold number. Okay. So this notation is just representative. You'd actually compute some of the point-wise errors associated with each data point in dval, where the data points in dval represent the actual x's. So if you had 100 data points here, maybe this would be x1 through x10, and this would be x11 through x20, and so forth. And this would be x91 through x100. Now I'm drawing them in order, but certainly you would randomize them in practice. So in k-fold cross-validation, that parameter k is the number of folds that you have, right? 10-fold, you're dividing by 10, and each fold is going to have k many data points in it, where k is equal to n over the number of folds. Okay, and so this strikes a happy medium so that you're not falling into the issue that happens when you have a large data set of size n. Because if n is equal to 1 million, if you were leaving one out, you'd have a million different versions of your training set. You'd have D1 up to and including D1 million, and that would mean you would train your hypothesis set on each one of these million many data sets, and then you would evaluate on each one of the million validation sets, compute the cross-validation error, and then make your selection. So you'd spend way too much time training, because it's unreasonable to train a hypothesis a million different times in order to compute cross-validation error. That would take way too long. So this cross-validation error using fold-based cross-validation error strikes a happy balance. And so rule of thumb, many people find 10-fold cross-validation gives you very good results. Okay, so with that, I finished the module, and we will end there.